This is the City of Canyonville's wastewater treatment plant. The City of Canyonville's wastewater treatment facility was originally constructed in 1955. The system consisted of an influent pump station, headworks, dual clarifier, trickling filter, and an anaerobic digester for solids treatment. The city undertook a major facility upgrade in 1979. The 1979 facility included a new grit removal system, new activated sludge system, and an additional secondary clarifier. With the old system, the city had many compliance and reliability issues that ultimately prompted additional improvements. Phase 1 improvements occurred in 2014. At that time, the city installed new influent screens, new grit removal system, new partial flume, and new influent pump station. The wastewater treatment plant is currently undergoing additional improvements to both the liquid and solid streams. The site is currently under construction, with construction operations currently focused on solids management infrastructure. The new liquid stream was commissioned about 3 weeks ago. We're currently viewing the influent screening system. Raw wastewater flows by gravity entirely to the wastewater treatment plant. The first process encountered is the influent screen system. The influent screen system consists of two shaftless rotating drum screws. There are two influent screens, each rated for 2.4 mgd. The influent screens remove particles 3 millimeters and larger from the waste stream. Removed solids are washed, collected, and taken to the landfill. After preliminary screening, raw wastewater flows by gravity to a vortex grit removal system consisting of a grit chamber, grit pump, and grit classifier. This is a forced vortex system that uses hydraulic forces to remove grit from the waste stream. Grit that is removed is sent to the classifier and then ultimately taken to the landfill. From the grit removal system, raw wastewater flows by gravity to a partial flume flow measurement system. The influent flow this time of year is approximately 120,000 gallons per day. During wet weather, storm events can peak up to peak day of 1.2 mgd and a peak hour of 1.6 mgd. The rated peak hourly flow capacity of this wastewater treatment plant is 2.2 mgd. This is the influent pump station. Influent wastewater is conveyed to a wet well that houses 4 pumps, 2 jockey pumps, and 2 large pumps. The jockey pumps manage influent flows throughout most of the year, typically outside of storm events due to infiltration and inflow. The influent pump station was constructed as part of Phase 1 improvements and pumps to a new secondary screen, which is part of the main wastewater improvements that are currently underway. This is the secondary screen. Proper preliminary treatment is really important for MBR treatment systems. Without effective solids removal, solids will collect and accumulate on the membrane surface, restrict airflow, and cause permeability issues. For that reason, the wastewater treatment plant improvements included the addition of a new secondary screen to remove particles larger than 1.5 millimeter. This improves the performance of the membranes considerably. The secondary screen is a side hill screen that processes influent wastewater that has already underwent removal of particles 3 millimeters and larger. Particles 1.5 millimeter and larger collect on the screen, accumulate, and slough off into a washer compactor. Sloughed solids are washed, compacted, and conveyed into a continuous bagging system for eventual landfill disposal. The side hill screen can be physically cleaned with a squeegee as material plugs the openings. This is a relatively quick maintenance process. Filtered raw wastewater then flows by gravity to an Inoxic tank. The Inoxic tank is the first step in the MBR process. In the Inoxic tank, preliminary treated raw wastewater blends with return activated sludge into an environment that is deprived of dissolved oxygen. The mixed liquor is mixed with a low horsepower mixer with a bridge mounted motor, as you can see in green. The propeller is submerged and rotates constantly to provide good mixing. The propeller forces the liquid in the tank to descend and creates a good circular motion and mixing in the tank liquid column. This is a low energy process with only a 2 horsepower drive motor. The motor is easily accessible for maintenance and inspection. The tank and all the process tanks in this MBR system are approximately 18.5 feet deep. The DO is currently less than 0.2 milligrams per liter and often close to zero. There is no forced aeration in this Inoxic tank. Heterotrophic bacteria populate the environment. Biological denitrification occurs in this tank, where nitrate is converted to nitrogen gas and expelled to the atmosphere. With the denitrification process, we also recover about 50% of the alkalinity lost during the nitrification process. This is helpful to reduce the possibility of dropping the system's pH. The nitrification process is optimized with a pH of approximately 7.5. Nitrifiers have diminished kinetics at lower pH values. We do have the ability, if needed, to add alkalinity to the Inoxic tank. A small duplex chemical feed package in the chemical room is installed to feed alkalinity into the system if the pH value drops due to nitrification rates and low influent pH alkalinity values. You'll notice fiberglass covers on the entire MBR process. All covers are removable and have access ports. The covers prevent falling debris from entering the process and damaging the membranes. After the Inoxic tank, mixed liquor flows by gravity to the PreAeration tank. The PreAeration tank has fine bubble diffusers that supply oxygen to the aerobic environment. This is where the majority of the biological treatment occurs for the MBR. We expect complete BOD removal and nitrification to also occur completely. We have an ammonia limit of less than 5.4 milligrams per liter during the summertime when discharging to the South Umpqua River. To ensure proper airflow, we have a submerged, continuous dissolved oxygen probe. It's located in the mixed liquor and measures the instantaneous DO concentration. We're targeting a DO of about 2 milligrams per liter. The pre-aeration blowers, which we will later see, have variable frequency drives that adjust the blower speed based upon the actual DO in the pre-aeration tank. Also, during the summertime, when discharging to the South Umpqua River, we have a low phosphorus limit. This time of year, the phosphorus limit is less than 1 milligrams per liter. To achieve this, we are injecting liquid alum into the pre-aeration tank to chemically precipitate phosphorus and remove it through the waste stream. To accomplish this, duplex chemical feed pumps located in the chemical room convey liquid alum to the pre-aeration tank for flocculation. We're now viewing the distribution channel. Highly nitrified mixed liquor then flows by gravity to the distribution channel. The distribution channel equally distributes the mixed liquor to the 3 MBR tanks. Slide gates are used to adjust flow and, if needed, take an MBR tank out of service. The MBR tanks have membranes installed. There are 3 tanks, MBR tanks, each with 5 rows of membranes. Each row has a lower membrane unit and an upper membrane unit. The membrane system consists of a coarse bubble diffuser system at the bottom of the membrane units. This provides not only air for additional biological oxidation, but primarily for scouring of the membrane surface. As the water is pulled through the membrane, solids are pulled onto the surface. Air scour is needed to remove solids from the surface of the membranes and maintain a proper flux rate. The air and mixed liquor flow through the membrane cassette much like an airlift pump, creating a well-mixed environment in each tank. Air is delivered to the coarse bubble diffusers from the stainless steel air piping. You will notice stainless steel air piping on both sides of the tank. Once a day, the coarse bubble diffusers are cleaned by opening an electronically actuated valve that pulls mixed liquor into the air piping and returns it to the distribution channel. This effectively scours the coarse bubble orifices to keep good airflow and membrane cleaning. Each MBR tank has permeate suction headers for the upper membrane cassettes and permeate suction headers for the lower membrane cassettes. Permeate is pulled from the membranes with permeate pumps in the control building. The permeate pumps filter the mixed liquor in production mode. The pumps operate for about 9 minutes and then relax for about 1 minute. This 1 minute relax period allows the membrane to relax and air to better clean the membrane surface. We currently have one MBR tank in operation as we grow mixed liquor. We will eventually commission all 3 MBR tanks. We currently have a mixed liquor of about 7,000 milligrams per liter. Our target mixed liquor is between 10,000 and 15,000 milligrams per liter. A 3-ton overhead crane was installed to provide the ability to remove the membranes if needed and to remove the RAS-WAS pumps if ever required. The membranes can be removed and transported to the cleaning pad adjacent to the MBR. Mixed liquor from the MBR tanks flows by gravity to the RAS-WAS channel. There are 2 waste-activated sludge pumps and 3 return-activated sludge pumps, all submersible, centrifugal pumps. The WAS pumps are designed to manage the mixed liquor and convey the sludge to the future aerobic digester. The RAS pumps recirculate highly nitrified mixed liquor to the Inoxic tank for pending denitrification. Also in the RAS-WAS tank is a pH probe. This provides a 4 to 20 milliamp input to the main MBR PLC to facilitate alkalinity feed rates based upon the instantaneous pH value. If the pH drops, feed rates are increased automatically. A pressure transducer is installed to monitor the liquid level in the RAS-WAS tank. The speed and flow rate of the permeate pumps is increased as the liquid level increases. As the liquid level lowers, the speed and permeate flow rate drops. During the nighttime this time of year, because of low flows and low I&I, the system goes into nap mode a considerable amount. For process control purposes, we have magnetic flow meters on both the RAS pumps and the WAS pumps. From here we will go to the permeate pump room. This room houses the pumps that pull suction on the membrane units for filtration. There is 1 permeate pump per MBR tank and 1 complete standby unit. The pumps are rotary lobe with a tremendous turn-down ability. We're currently operating 1 MBR tank with a permeate pump that runs about 200 gallons per minute at the low setting. Each pump has a capacity of about 566 gallons per minute. They're all 15 horsepower pumps. Each pump has a flow meter, turbidimeter, and pressure transmitters. The suction side pressure transmitter monitors the transmembrane pressure, or the TMP, which is an important operational parameter for membrane operation. The turbidimeters measure the permeate turbidity continuously and relay the information back to the main MBR PLC. If the value is over a set point, an alarm is activated. This is the main control room for the wastewater treatment plant. In here we have an automatic transfer switch for the standby generator, an active harmonic filter, motor control center, the main MBR PLC, UV disinfection system panel, and other panel boards. The MBR PLC includes a large touchscreen and SCADA interface. This interface offers the ability to monitor the entire wastewater treatment plant from the influence screens to the MBR and UV disinfection system. In here we can review trends, adjust set points, analyze alarms, and perform many other functions. Also in the control building is a chemical feed room, which we will access from around the building. The chemical feed room consists of an alum feed system for chemical precipitation of phosphorus. The alum feed system includes 2 dosing pumps. The operators can run off of a 405-gallon day tank or totes. Also included in the chemical room is the alkalinity feed system that is connected to the pH probe in the RAS-WAS tank. This feed system has 2 diaphragm pumps that are used to feed caustic soda into the wastewater if the pH drops to non-optimal levels. The system attempts to stabilize. The chemical room also includes a chemical clean-in-place skid for the MBR system. Typically, once or twice per year, the membranes are cleaned in place with a very low concentration dose of sodium hypochlorite. The low-dose sodium hypochlorite is injected with a Venturi injection system. The total volume delivered is managed with a magmeter. We will now head over to the blower room. The blower room houses the PreAeration blowers and the MBR air scour blowers. There are 2 PreAeration blowers, one duty and one standby. They manage the dissolved oxygen in the PreAeration tank to accomplish the 2 milligram per liter set point. The air is adjusted based upon the airflow sensor, a thermal mass airflow sensor, installed on the discharge line of the PreAeration blowers. The MBR air scour blowers are much larger, at 50 horsepower each. There are 4 blowers, one for each MBR tank and one for standby. The blower piping was designed to allow the standby blower to deliver air to any MBR tank. The MBR blowers each have flow sensors to manage airflow to the MBR tanks. All of the blowers are rotary lobe type, also with a considerable turn-down ability. From the MBR system, we will now venture to the UV disinfection system. Permeate from the permeate pumps is pumped through a 10-inch diameter force main to the UV disinfection system. The UV disinfection system is a non-contact style UV system. Permeate from the MBR system travels through tubes. The water does not come in contact with the UV bulbs. The bulbs themselves are in structures on racks. The UV unit is flow-paced. As the flow rate increases through the units, the liquid level in the UV unit increases and the corresponding number of UV lights activates. If the flow rate stops, the UV bulbs are turned off, and if the flow rate reaches a certain set point, all of the UV lights are activated. The UV intensity is continuously monitored in the unit, as is the UV transmissivity. UV transmittance is the percentage of incident ultraviolet energy that is directly transmitted through the water. With the high quality treatment achieved with the MBR, our transmittance is generally really high. Also included in the UV system is a temperature probe that continuously monitors the effluent temperature and logs it for discharge monitor reporting. An automatic sampler is included that pulls effluent after the UV system. The sampler is configured for flow pacing mode. At this point, the effluent is ready for discharge to the South Umpqua River and flows by gravity through a non-potable water tank and then to the outfall. Effluent quality is typically very good, less than 5.5 BOD/TSS, very low ammonia, and non-detect E. coli. The non-potable water system provides treated water to the plant for several process areas, including MBR clean-in-place process. The non-potable water system includes 2 vertical turbine pumps, each 7.5 horsepower. They maintain a pressure by using VFDs of about 70 to 80 psi. A flow meter measures the non-potable water used at the plant. To maintain plant operation during power outages, we installed a new standby generator. This provides power to all critical components during a power outage. It's a 500 kW unit and diesel powered. This is the new operations building. The city previously had a confined lab, which also was their main electrical room. The new operations building consists of a new lab, new office, new restroom, new break room. This provides the city with much needed space for system operations. The operations building includes a dedicated computer for access to SCADA. Operational staff are currently moving into this building and tasked with closely monitoring the switchover to the MBR. Construction operations are currently focused on solids management systems. Waste-activated sludge from the MBR will ultimately be conveyed to an aerobic digester. The city's previous activated sludge system will be converted to an aerobic digester with a membrane thickener. The aerobic digester will include an air diffuser system and pH probes for aeration control. Thickened solids from the aerobic digester will typically be sent to a dewatering building. The dewatering building is currently under construction. It will ultimately include a new screw press, blowers for the solids treatment systems, and a loading bay for collecting dewatered solids. Digested solids from the aerobic digester can also be sent to a biosolids storage tank. This tank provides additional stored solids capacity, which can also be pumped to the biosolids dewatering facility. It includes an access platform, a biosolids transfer pump, air diffusers, and other ancillary components. This is the final stop in the tour of Canyonville's wastewater treatment facility. As you can see, there is still a fair amount of work to be completed for the solids management systems.